Great. Thank you very much. Before I start, I want to thank EERI for organizing this seminar series, especially Jay and Maggie. They spent tremendous amount of time in background and organizing, and we really appreciate their efforts. I'm going to go, as Jay told you, I'm going to go and give you an overview of what's going on, a little bit background and introduction. NGA-West2, we call it as a mega project. It has a bunch of specifically 8 sub-projects or tasks, if you want to, but really each task by itself is a project. I'm going to have a few slides for each sub-project, the status of NGA-West2 and people involved. I show you this slide, just I know everyone knows, just to put it in perspective where we are. Probabilistic seismic hazard analysis, PSHA, is now has been going on, is now a standard tool for around the world. In order to do PSHA, you need basically 2 pieces of important information. First of all, on the left, you have to know something about the seismic sources. You have to know about the geometry of the faults, rate of activities, background seismicity, and so on. So you have to know something about seismic sources. And then you have to know something about ground motion prediction equations or attenuation models and so on that I'm going to talk about. And then you put together the package and you get the results of PSHA, probabilistic seismic hazard analysis. Top right is what we are going to talk about the whole seminar today. Ground motion prediction equation, GMPE. This is not really my favorite name, but since we started and we coined the name 10 years ago or so, now we are keeping it. The reason that I personally don't like it, because we are not predicting anything, first of all. Also, it's not really an equation, it's a model. Those of you who have done modeling, you know that it's modeling a bunch of things involved. We used to call it attenuation. Some people really seriously, they don't like this term correctly, because attenuation is really decay of the amplitude with distance. Now it's not only distance, we have lots of other things involved that you are going to see. It's magnitude, the solar faulting, soil condition, and so on. It's really ground motion model. It's a model building process, and it's really a set of scaling rules or relations that you need. Even if you don't use GMPE, you need to know how the ground motion is increasing, decreasing with various variable or parameters like magnitude, distance, and so on. Scaling, various scaling, very important. So we read what we see from the nature and we try to model. And also uncertainty is a really important part of ground motion prediction equation. Uncertainty that we don't know really how the nature is behaving, and also uncertainty among different models or lack of knowledge. So uncertainty is a really important part of GMP. The latest developments and advances in GMP are really coming from NGA projects. NGA, you know it, but just in case, is next generation attenuation. NGA relations, I told you that we don't like attenuation term, but again, 12 years ago, someone in our community started this one. We are using NGA. It's next generation attenuation, is really GMPE. There are 3 separate NGA projects at the Pacific Earthquake Engineering Research Center here. All of these really are multidisciplinary programs with numerous people involved. Really, we have undergraduate students, graduate students, postdoctoral fellow, as you go all the way with senior researchers with 30 years or plus research. It's not really only an academic exercise, it's really combination of academic researchers as well as practitioners. Practitioners are really integral part of this thing. We interact very, very closely. And very importantly, also we use on really daily basis interaction with end users. This is not a typical National Science Foundation proposal that you get $20,000 and then after a year you write a couple of papers and publish it. This is not really the purpose of these things. End users should not be surprised by the results at the end of the project. End users are heavily involved in daily basis. We get feedback from them, really what things are important for end users, and interaction is important. One other thing which is very important, we are totally really convinced that this has to be a combination of earth scientists and engineers. So this is not, decades ago it was really, when Newmark was around and Hausner, it was only engineering part. Then it switched to earth scientists. Now we are convinced this is an interaction between earth scientists and engineers. That is really the key. I mentioned there are three separate ongoing NGA projects at PIER. First is ground motion prediction equation for shallow crustal earthquakes in active tectonic regions. It's like California. So California, Taiwan, Middle East, a part of Japan, really that is the part. This is what we started first more than 10 years ago, and we are talking today about. Then after the unfortunate disaster in Japan, Tohoku earthquake, we started another very important project, subduction. Now we call it NGA-Sub. We are in early stage of that project. We are collecting thousands of data points from Japan, from Chile, and so on. It's very important, but we just started a couple of years ago. We have a few more years to go. It's important, obviously, for Pacific Northwest and also Northern California, and obviously in Japan, Chile, and so on. Then a few years ago, we started another NGA project for so-called stable continental regions. Basically, in the U.S. is east of Colorado. Very important, although seismicity is very different. They don't get magnitude 7 and 8 every day, obviously, but it's very important. About 100 nuclear power plants in the U.S. are east of Colorado. So very important for nuclear community. Literally about 200 million people in the U.S. are affected by that project. Is Central Eastern North America, as well as like most of Europe, South Africa, and other places. NGA-West is what we are going to talk about the whole day today. Just to give you a background why we call it NGA-West2 versus West1 and so on. We started in October 2003. It was a kickoff meeting about NGA-West. At that time, we called it NGA-West. We didn't know that we are going to go to NGA-West2 and so on. Now we call it NGA-West1. We started a relatively large program, as I mentioned, for development of ground motion prediction equations for shallow crustal earthquakes in active tectonic regions like California, West Coast, and with many numerous supporting research projects. We started 2003, we finished it in 2008. GMPE, ground motion prediction equations, were developed, finalized, and then U.S. Geological Survey assembled a large review national team. They call it Tiger Team. Really, it was, I think, Mark knows, I think 20 people or so. They reviewed and they put everything under microscope, from the data as well as analysis results and so on, and eventually they adopted 3 out of 5 NGA-West1 models to the national hazard maps. That's the current version of the maps that you have. And then after the NGA-West1 was completed, we started NGA-West2, which is basically a follow-up. Before I go to the details of the NGA-West2, I really like to acknowledge the sponsors of the NGA-West2 project. California Earthquake Authority, CEA, insurance, earthquake insurance, very important supporter of the project. They really should be awarded because they funded 2 important projects that they contribute to the building code. One is our project, NGA-West2. The other one is about source characterization mentioned Yousef, that Mark Peterson is going to talk about. Two important projects that they will be the foundation of any seismic design and evaluation that you want to do in California. Caltrans, California Department of Transportation, has been supporting Peer Lifelines program since decades ago. Very active partner with us, Pacific Gas and Electric Company. This building started supporting Peer from day one. And in fact, before even officially Peer became a national research center in 1997, with the leadership of Lloyd Clough here, Peer Lifelines program was initiated in 1996. A little bit before that. So PG&E has been supporting on various projects Peer Lifelines program. Now, that was a little bit background about what's going on. Now I'm going to show you a few slides for each sub-project under NGA-West2. One of the most important sub-projects that we have had for NGA-West2 is compiling a large, very comprehensive, well-QA'd ground motion database. And from now on, I'm talking about only shallow crustal earthquakes. So I'm not talking about subduction, Tohoku data, and so on, although we have collected, but it's totally different in subduction. I'm talking about California type, Middle East type, Taiwanese type earthquakes, shallow crustal earthquakes. I mentioned officially Peer started as a national research center in 1997. This is a plot of what we had in 1997. Vertical axis is magnitude, horizontal axis is distance. Each point really is one recording station. This is what we had in 1997. In NGA-West1, we added more stations. So NGA-West1 database was collection or collective of the red and blue dots. So the size of database increased tremendously under NGA-West1. At NGA-West1, the largest magnitude event that we had was magnitude 7.9 in Alaska, Denali, but only few stations. That's what you see, 7.9 top of the line. Then in the current project, NGA-West2, that we started, we added tremendous amount of data. This is from magnitude 3 to 8. Let me go back. This is what we had. This is what we have. The new database is collection of all these colors that you see. Overall, we have about 63,000 individual records, or 21,000 three-component recordings. The size of database increased by almost factor of 6. I truly believe this is the largest uniformly processed ground motion database in shallow crustal earthquakes in the world. It's very comprehensive, it's very rich for various applications. And again, Tim and Cheta, who was postdoc with us for 2 years, he worked day and night and weekend, thousands of hours, not alone with others also. He's going to go over the details of the database, but I'll show you, I'll give you an overview of what's going on. So this figure is from magnitude 3 to 8, just to make sure that I'm not overwhelming you with the small magnitude data. In this one, I show you from 5 to 8. And this is what we had in NGA-West1, collection of the blue and red dots, and this is what we have. So even from magnitude 5 to 8, the database is becoming absolutely rich. One important feature that you see now, magnitude 7.9, we have another earthquake, Wenchuan in China, is very relatively well recorded with various efforts that all of us at Peer, we signed MOU and so on with Chinese. We got almost all the data that they had with 64 aftershocks with very good soil profile. Every one of these, it takes lots of effort even to get the data, especially foreign earthquakes. We get the data, then process the data. So this is what we have from magnitude 5 to 8, very rich database. This is a summary of the main earthquakes, key earthquakes data that we added in the NGA-West2. In NGA-West1, we had only one earthquake in Japan, and when I said Japanese earthquake, I'm talking about only the shallow crustal aspects, not Tohoku type, not subduction. Japanese, they have both types of earthquakes. In NGA-West1, we had only one data from Japan, Kobe, 1995 earthquake in Kobe. Then in NGA-West2, we added a bunch of very well recorded earthquakes from Japan. The latest earthquakes that we have are two sequences of earthquakes in New Zealand, Darfield and Christchurch. These two earthquakes became very important, not only from the database, but from the technical point of view, that they raised a bunch of very, very important issues, technical issues that I'm going to elaborate later. As I mentioned, the largest magnitude that we have is 7.9 from Wenchuan, as well as from Alaska Denali earthquake. This shows what we had in the second row is what we had in NGA-West1. The third row is what we have in NGA-West2. Obviously, the number of earthquakes, the number of records are increasing a lot. I'm going to get to the details of RotDnn and so on. Don't worry about that for the time being. I'll get into that in a minute. In NGA-West1, we had everything for 5% damping. Now we are going from 0.5% to 30% damping. So we have 11 damping ratios by itself, so 11 times the number of sizes of the flat files and databases and so on increased. In NGA-West1, we went also all the way to 10 seconds, period of 10 seconds. In NGA-West2, if possible, if the record was not noisy, we went to 20 seconds. So the data that I'm going to mention in a few minutes, the database that is already released, you get the spectral ordinance up to 20 seconds. However, our ground motion prediction equations, we are going up to 10 seconds. Going beyond that, I'll mention later in the afternoon, we need to do a little bit more technical efforts. One other change that we made, and again, it's not a big deal, but it's doing something better, is so-called intensity measure. In traditional, like 30 years ago, so each earthquake, suppose is recorded at a recording site, recording station, it usually records 3 components. For horizontal components, 30 years ago, we used to do geometric mean of the horizontal components, which is a square root of H1 times H2. This was a while ago. Then in NGA-West1, we did something else, GMROT-I50. Don't worry about the details of that, because when you put everything into the pot, the difference is really only a few percentage. It's not a big deal. In NGA-West2, we went to something else that I'm going to mention in a minute, is RotDnn. Again, don't worry about the details of that unless you're really interested and come and ask me about it. When you put everything, thousands of data points into this pot, the difference between geometric mean, GMROT-I50 and RotD50 are close. But individually, they are different. Why did we switch to this? As I mentioned, earthquake happens at each recording station. We record 3 components. Right-hand side rule, we had it in elementary school. So we have 2 horizontal components. We resolve these 2 horizontal components and we rotate the horizontal components 1 degree at a time. And at each period, we find the maximum, we find the minimum, and we find 50 percentile at each period. The maximum is, we call it RotD100. So RotD100 is basically rotated motion 1 degree at a time once you find out the maximum. The minimum is RotD0. 50 percentile is what we are using. Why did we use it? Why we did switch to this new intensity measure? After we finished NGA-West1, our friends in building code community switched from geometric mean to maximum rotated motion, which is basically now in our new terminology is RotD100. So that was after NGA-West1. So we thought that in NGA-West2, at least we go with RotD50, which is in the same family. Now, at least they're all in the same family. RotD100 is what building code community is using. RotD50 is what ground motion community is using. What other thing that we did for the database was that we went back and reprocessed all the records in NGA-West1 to widen the usable frequency bandwidth of the records. So one by one, many records in NGA-West2 was reprocessed. They increased the usable bandwidth, the reliable period range that you can use it. This shows number of records, vertical versus period. The blue is what we have in NGA-West2, and the red is what we had in NGA-West1, the same database, but reprocessed, and number of records, reliable records at long period increased by factor of 2.5. So, in summary, for long periods, we have much more reliable database. That is one, we believe that's one reason that when we get, by middle of the day, you see the standard deviation at long period now reduces. We believe one reason is that we have more reliable long period ground motions. That was another effort related to database. We added more than 10,000 small magnitude lower than 4.5, mainly in California. I never thought in my life that I'm going to work on magnitude 3 because no engineer really cares about that. And we, in NGA-West1 even, we said, who cares about magnitude 3, 3.5? Why did we add so many thousands of small magnitude data from California? 3 different reasons. The main one is that literally after a month or so that we finished NGA-West1, we heard from our friends and colleagues, especially in Europe, that they compared our NGA-West1 models with small magnitude data. Remember, most of the world, they don't have magnitude 7 and 8. They have magnitude 3 and 4. So they compared their recorded small magnitude data with our NGA-West1 model, and we knew that we were over-predicting small magnitude data, but we said, who cares? But when they compared their data with our ground motion prediction equations, and we knew that we were over-predicting, they scaled down the entire GMPE even at magnitude 7, which is absolutely dangerous and wrong. So immediately we jumped and sent emails and we met with them, don't do it. That created really a great motivation that if people starting comparing their small magnitude data with our GMPE is going to be a very dangerous situation. As I mentioned, we were over-predicting a small magnitude up to 6, 4.5, 5 or so, and now we are, by adding lots of data, we are shaving that over-prediction. There is another motivation that if you want to really put it under microscope, the standard deviation or variability of the ground motion and a specific station, you need that station to record multiple earthquakes. In order to do that, fortunately or unfortunately, since we don't have magnitude 6, 7, and 8 every day, we don't have multiple magnitude 6, 7, and 8 at that station. But we have magnitude 2, 3, 4 almost every day. So if we go to a small magnitude data, it's possible to have single station, single recording station with multiple events. If we do that, you go through simple statistical analysis and find out a specific variability of the ground motion at that specific station. In other words, you are going to identify a specific standard deviation at different sites. So we are working on that. Basically, the next generation, that is the way that we want to do. We organize our data. In order to do that, we had to go to a smaller magnitude. The other part is that preliminary analysis showed that there can be a little bit regionalization between the ground motion, especially between Northern California, Southern California, and then other parts of the world. If you want to compare that, again, you need a small magnitude. You cannot, we don't have magnitude 7 and 8, Northern California and Southern California, so many. So we went to a smaller magnitude to compare various regions. So this is left-hand side is for peak ground acceleration. Right-hand side is spectral ordinate at 0.1 second. Vertical axis is acceleration. Horizontal axis is magnitude. This is basically a scaling of the ground motion with magnitude. This is the part that really we wanted to adjust and reduce the conservatism and over-prediction. And I'm going to show you, I think we did a good job on that. Database, still I'm talking about database. VS30 is average shear wave velocity in the top 30 meters of soil. It's an index of the soil characteristics. It's not maybe the best parameter in the world. It is still challenges and discussions among the geotechs that what is the best parameter, but it's one index. It's better than all the days that we used to say rock versus soil. At least now we have a quantified, well measured. VS30, this is a number of sites, vertical axis versus VS30 values. This is what we had in NGA-West1. You see the measured VS30, it was a small percentage of the overall database. It's still a small portion of the database, but tremendously now since we have more data. There was a working group under NGA-West2. They did lots of analysis of the estimation of the VS30 at various sites. If we don't have measurement at the site, we have to estimate it. For 2-3 years, a group of geotechs work on how to estimate VS30 based on different methodologies, and this is what we have. Still, a good portion of the database, VS30 is based on estimation, but the number is really increasing by huge amount, and the quality of the data points are much better. Now, flat files. Flat files really are Excel files. The reason we call it flat file is that there is no such a thing that you click here and you go to another data, and then you click it there, you go to another file. Everything is here. It's basically an Excel file, with about 300-400 columns and about 21,000 rows. This is what everything that you need to know about the GMP. This is what we used. The flat file, about a couple of hundred columns of the Excel file are metadata. Metadata really are data about data, characteristics or attributes of the data. Data really is a spectral ordinate, as I mentioned, at 103 periods, plus background acceleration, velocity, and so on, and metadata. The part that, just to give you a perspective, the part that is really labor intensive and it takes lots of effort, it's not really the data, it's metadata. Estimation of VS30, calculation of distances, then we found out that the location of instrument was a little bit off, the hypocentral date was a little off, and so on. So it took tremendous amount of effort by many people to make it, to reach this data and base and flat file to the level that we are relatively comfortable with. But there is no perfect database. I'm pretty sure there are some minor errors here and there, but hopefully the errors and typos are not major, because it went through many iterations and QA. Flat files are publicly available. This is what we're really proud of it. Everything is transparent. There's no hidden file that we have and you don't have it. You have exactly all background data that we use for our development of GMPE. You can download the flat files from peer website. There are 11 of them for 11 damping ratios. The spectral ordinates are what we use for development of our GMPEs, or RotD50 spectra. These are the data that we use for development of GMPEs. From day one, 10 years ago, that was the real foundation of our work, intellectual foundation, that if we develop GMPEs, we should give the data to the world that they can check our work. It's not that they say, trust us, we use very good data, and these are the results. That's not the way we work. It's perfectly transparent, 11 of them for 11 damping ratios. So that was exactly what we used for the development of GMPs. However, a side issue is that we collected so many thousands of waveforms, time histories we used to call it. Now, some people seriously they hate the word time histories, because time and history are in the same category. So time series is the same time history. So People ask, engineers and others, they ask about time series, the actual recorded motion. We are updating our online database. You know that we have a very, very popular online database that you go there, you enter your various combination of parameters, and you enter, say, 100 recorded motion. You use it for various engineering or loss estimation applications. It's a very popular database. Our servers currently are at Richmond Field Station, 10 minutes north of University of California at Berkeley, and okay, there are lots of constructions going on there, and occasionally we get power outage. Servers are down. Before our staff tell us that the power is out and server is not available, literally, Steve Main and I will get emails from South Africa, from Germany, from all over the world that, oh, the database is not available. And then we found out that the electricity is out. So it's extremely popular database. It's free. You can download the response histories and so on, the time series. As we speak now, you can access to NGA-West1 time series. Spectra is available for NGA-West2. Time series, we are working very hard. Sylvia is working very hard with IT person. In the next, hopefully 1 month, we are pushing by end of the year, we are going to link all the NGA-West2 database to online that you can download it, and then we have a dream for the next couple of years to make more features. It's a very, very popular tool in the community. Then I want to make a point here. Database development, there is a misconception that there is a database group. They work on the database. Once it's final and 100% is good, they pass it to a different group. That's not the way it works. It used to work 30 years ago when we had 200, 300 data points. That a group developed perfect database, pass it to another group. It's not really working these days. We have 20,000 records. So everyone working together. There is a working group on the database. They develop something not 100% accurate, but they show it, and the analysts and GMPE developers, they dig into that. And routinely they find errors. They send it back, they say, oh, the hypocentral depth is wrong, this is not, they modify it, pass it, and we go through that iteration hundreds of times. So the GMPE developers are really essential part of database development. Although cranking the numbers and so on, there is a specialized group of engineers and seismologists and so on, but it becomes mature and mature enough the database through really hundreds of iterations over the years. Once the database reaches to the level that we think there is no serious major error in it, then the GMPE developers start developing their models. Parallel to this effort, there are 2, 3, 4 other research activities going on. One was related to directivity of ground motion. I'm going to show you a slide. There was an effort on the modeling of hanging wall, foot wall, updating nonlinear soil response, and classification of main shock versus aftershock. So these were parallel to each other. As I mentioned, the 5 teams of GMPE developers, not only they contributed on daily basis on the development of the database, also they started doing modeling. 5 teams, Abramson and Silva used to work together since 1997. Now they added Ronnie Kamai. She's working with them. Bohr and Atkinson, they used to work together for decades. Now they added 2 new partners. John Stewart at UCLA and Emil Seyhan, formerly at UCLA, now a postdoc at Pierre. Chen and I have been working for now almost 30 years together. Brian Chow and Bob Young, they have been working together since 1997, and Professor Idris. 5 teams dig into the various data and developments. The scope of horizontal ground motion prediction equations, as I mentioned, we are using a sort of average of 2 horizontal components. Now we call it RotD50 for intensity measure. The scope of GMPE was to develop GMPEs for peak ground acceleration, peak ground velocity, And as a minimum at 21 periods that I listed here, from 0.01 second all the way to 10 seconds, we have a spectral ordinate at 103 periods, more than 100 periods. So the GMPE developers, they could develop ground motion prediction equation for 100 period, but as a minimum they should really do it at these specific periods that are important for the entire community. We have the data for peak ground displacement in the flat files. You have the numbers, peak ground displacement. After lots of digging into the details of that, we found out that peak ground displacement is very, very sensitive to the details of record processing and filtering, and it's not a reliable parameter that we spend time to develop GMPE. So we don't have GMPE for ground motion for peak ground displacement, although the numbers that we believe are not reliable and our numbers are very sensitive to details of the record processing. We give it for other applications. Scope of ground motion prediction equations. This is an important point to make. I showed you that we have data up to magnitude 7.9. That's what we have. Fortunately or unfortunately, in the world, we don't have recorded ground motion for shallow crustal earthquakes. I'm not talking about Tohoku and so on. Shallow crustal earthquakes, we don't have more than magnitude more than 7.9. 30 years ago, we used to do it like this, that this was the range of the data, and we had large disclaimer, oh, don't use it beyond this and don't use it beyond this. And we figured out that no one even reads the disclaimer, and they use it beyond the range that we recommend. So instead of closing our eyes, even our data really up to 7.9, we know people use it. We know Mark Peterson and others, possibly they use it for larger than 7.9. So we at least analyze to make sure that beyond the 7.9 data that we have, the behavior of GMPs, they make sense. We didn't just stop and close our eyes. So the scope is at least look at the scaling of your GMPE up for strike slip for up to 8.5, magnitude 8.5 to reverse magnitude 8 and normal 7.5. We used to go from distance from 0 to 200 kilometers based on input that we got from the users, Mike Peterson, US Geological Survey, as well as specific projects. There is a nuclear power plant in Arizona that they get motions from San Andreas Fault, so more than 200 kilometers. So the request was that we go to 300 kilometers. So we are now, most of our GMPs except one, it goes to 300 kilometers. There is one important piece that this was the overall coordination among five GMPE developers. We gave them the framework. However, intellectually, there's no way that we force them that you have to use up to 300 kilometers, you have to use this, and so on. It's really up to them to decide what part of database they use, but they have to justify, and they have to have a reason. One good example is using aftershocks. There are a couple of GMPE developers that they didn't include aftershock in their analysis. Now, statistically, we understand that if you have a main shock, hypothetically magnitude 6, and you have an aftershock, hypothetically magnitude 6, the ground motion, even the magnitudes are the same. Ground motions overall can be different. And a couple of GMPE developers, they said the important thing for the community and for us is main shock. We don't want to miss the main shock. We didn't include aftershock. A couple of other GMPEs, they said, no, we can use aftershock, especially for site response. Even the magnitude scaling and other things are different. They used it. We left it to their really expert judgment, but they have to justify, exactly as I mentioned. That was one example, and there are other examples. That was what I just mentioned. They can select a subset of the database, but they have to justify. For example, another good example is abutment dams. We don't have so many rock sites, as later on you're going to see, unfortunately. So a couple of GMPE developers, they said, oh, as a minimum, we include rock sites close to dams. A couple of other GMPE developers, they said we get the response of dams in that, we are not going to use it. So it's really a model building process with some selection. I show you only 2-3 slides of comparison. Nick Greger is going to show you more slides of comparison. This is 5 GMPEs that you can see, and this is peak ground acceleration versus distance for magnitude 7 strike slip at VS 3760 meters per second. Not drastically different. This is for spectral acceleration at period of 1 second, not too bad. This is versus magnitude scaling. They look the same, but if you really look at it around magnitude 6.5 or 7, you see there are some differences. At the specific size, these differences can show up importantly. This is for a specific example. I want to make a point. This is for Campbell and Bozorgnia. Peak ground acceleration versus magnitude is magnitude scaling. The red is what we had in 2008. The blue is what we have now. The point that I'm going to make is this. So by adding thousands of small magnitude data, we could reduce the conservatism and over prediction at a small magnitude range. And also the other point that I'm pretty sure most of you are familiar is that at short period, like PGA and at short period spectral ordinates, the scaling of it versus magnitude is not a straight line. In the modern GMPE development based on other inside information from seismologists, 1981, Ken Campbell proposed this so-called saturation, that the magnitude scaling is not linear. In 1981, that was not unanimous. The community was not supportive of that concept. Ken pushed it. Now, really, I should say that everyone is using this concept. At higher frequency, short period magnitude is not linearly scaled, which is a good thing. Otherwise, it would have been very difficult to design if you just increase the magnitude and ground motion increases monotonically. So magnitude saturation, all models, they include magnitude saturation. This is a slide that I borrowed it from Nick Greger. He's going to have more slides. This is comparison of 5 GMPEs. Spectra, response spectra versus period, strike slip, 760 meters per second, magnitude 7 at 10 kilometers. Not drastically different among each other, strike slip. Then you go to reverse hanging wall. Now you see the spread. Because when you get to the hanging wall in football, there are more modeling issues involved. A couple of developers, they use simulation-based hanging wall model, although they regressed it against the empirical data. Others, they use other modeling parameters. So this dispersion and variability model to model variability, or so-called epistemic uncertainty, is there when you get to reverse faults on top of the wall, fault, which is really a hanging wall. Standard deviation, as mentioned, is very important, especially in our building code application. You go to 2,500 retain period, or for nuclear application, you go to 10,000 or longer retain periods. The standard deviation really contributes to the response. Now, standard deviation is function of magnitude in most of the models. Below 5.5, you get 1 standard deviation. Above 5.5, right-hand side, you get different standard deviation, and 5 standard deviation. These are total standard deviation, but I don't want to get into the details of between event and within events, but we have it for 4 out of 5 models. All I said so far was related to horizontal ground motion. We didn't have anything in NGA-West1 about vertical component, but as the ground moves, obviously, we have 3 components. I'm going to show you 2-3 slides just to give you a background, because vertical ground motion is a little bit new than what we are doing in NGA. So this is a plot of the ratio of vertical over horizontal spectral ordinates, V over H versus period. This is an older study in 2004 that we did it. The ratio for short period close to the fault can exceed tremendously more than what Professor Hausner in 1950s recommended 2/3. When you get to longer period, the ratio is less than 2/3. One really recommendation, it has nothing to do with NGA, but we confirmed it. Don't use 2/3. It has no foundation, scientific foundation. The data doesn't support the 2/3. It comes from a long time ago. We can do a better job. I have been working on this issue of vertical ground motion for at least 2 decades or even longer than that. I have heard from very famous structural engineers that vertical ground motion is high frequency, a structure is flexible. Structures are flexible in horizontal lateral direction. Unfortunately, structures are stiff in vertical direction. And the peak of vertical spectrum is also around that. The effect is out of my scope. Maybe the effect is not important, but that's the reality. And the other reality is that all structures obviously are designed for 1G downward, which is the gravity. So you have to put it in perspective. If you're 80 kilometers from the fault and you get a vertical spectral ordinates of 0.05 G, it means it's 1 plus minus 0.05. So maybe it's not important. But if you get very close to the fault, that can be important. And I mentioned you have to see the perspective of the whole thing. So this is again pre-NGA, but I want to show you that at least you know what's going on. After decades of debate, eventually in 2009, NEHR provisions, there are a few pages at the back that we recommended development of vertical design spectrum based on horizontal spectrum that spectral ordinate at short period that we read out of natural hazard maps. So my point is this: if you don't know anything else, instead of using 2/3, you go to read out of natural hazard maps the horizontal spectrum. Put it in this perspective. We gave coefficient. At least construct something like this. Is better than 2/3. Everything, as I mentioned, was pre-NGA. It was even pre-NGA-West1. We didn't do anything in the last few years until NGA-West2. Now we have 4 brand new GMPEs for vertical ground motion. This is the first time NGA is addressing vertical ground motion. There are 4 teams. The names are shuffled because people work with different efforts in the vertical. 4 GMPEs, brand new GMPEs are ready to go. This is plot again is coming from Nick Greger. Left-hand side magnitude 7, right-hand side magnitude 8. Spectral acceleration versus period. 4 new GMPEs, and this is for strike slip 760 meters per second. One interesting thing I want to show: this is vertical over horizontal spectral ratio. Left-hand side magnitude 7, right-hand side magnitude 8. 5 GMPE models. This is for 760 meters per second. Vertical axis is in log scale. So it's less than 1. That is good. But it's for 760 meters per second. You go to 50 meters per second, the ratio is more than 1. This is qualitatively is consistent. We had over the last literally 25 years. Qualitatively, when you get it to a soil site, V over H, especially at high frequency, is becoming more than 1, especially if you get close to the fault. Qualitatively, we are consistent. As I mentioned, 4 GMPs for vertical component are final. We are editing literally the day of editing the peer report with 4 chapters on these things. We are really pushing by early next week. We are going to editorial and formatting and so on. We want to post it at peer website. So I talked about horizontal ground motion. I talked about vertical ground motion. Everything so far was about 5% damping. 5% damping is only a reference. You know, depending on the level of input motion and a structural system and so on, it easily can deviate from 5%. Professor Main did testing of single-family homes a while ago at Shake Table, Richmond Field Station. Depending on the level of input motion, can be 7 to 13% damping. So 5% really is a number, just a reference number. How do we scale it? As we speak, the entire community is still under influence of great work of Professor Newmark after decades, with some modifications, obviously, but we thought we can do a better job. We have huge database, we can do a better job. So Dr. Sonaz Rezayan, who was a postdoc with us, with her group, and now she's with the USGS working with Mark Peterson, developed a damping. So this plot shows a response spectra for less than 5%. Less than 5% is blue, so is more than red. Red is for 5%, and for greater than 5% is in black, so it's below that the red. So she developed a model. The model is basically a damping scaling factor. It's a set of factors that you need to apply these factors to 5% damping to scale it to the damping of your project. The model is a function of damping ratio, obviously. If it's 5%, the damping scaling factor should be 1, because all the GMPEs are for 5% damping. It's also a function of magnitude and distance. One important feature, we know fundamentally the duration is important, because number of cycles become increases, and obviously damping is a representative of energy dissipation. If you have more cycles of this energy dissipation, so you get larger damping. But in order to simplify that group, working group went through lots of analysis, and they took care of effect of duration by including magnitude and distance. So once they took care of magnitude and distance, they checked it against duration, we are okay, we are in good shape. Damping scaling factor, you have to be careful, is not the same for horizontal and vertical ground motion, because the frequency contents are different. So the working group developed 2 different models. This is the plot of magnitude scaling factor versus period. The black is for vertical, for red is for horizontal. So we have 2 models, same functional form, but 2 different sets of coefficients. The Excel file is available, the report is available. You don't have to do anything. And we are going to incorporate this as part of what ML is going to show in the Excel file. So in other words, the new Excel file, you are going to enter magnitude, distance, and so on, everything else, and the damping ratio that is desirable for you. 2.65, it gives you the response spectra, weighted average of 5 GMPEs, based on your decision, at that damping ratio. That's another new feature. Directivity. We know that directivity obviously is important. This is a plan view of the fault of 1994 Landers earthquake in Southern California, very famous earthquake in California. The fault is shown, and also there were 2 recording stations, Lucerne Valley, very close to the fault, and as well as Joshua Tree. Even by looking at, you see the epicenter and the direction of the rupture. Even by looking at this, you see the recorded velocity, the recorded motion. This is velocity plot. At the Lucerne is different than what at Joshua Tree is. Effect of directivity we know is important. We assembled a working group of 5 directivity modelers. These are really the best brains in the world that they have been working on this for decades. They work very hard. They developed 5 directivity models. The report is out, and if you like to use it, you're welcome to use. The report is out. Paper is out. The directivity models, they resulted relatively consistent results for a strike-slip fault, but they get different results for complicated bent faults and reverse faults. The work of directivity will continue in 2013, 2014. The next step, now we have good directivity models. The next step is that to adopt these directivity models, put it under a part of GMPEs. We'll do it in the next phase. Polarization or directionality of ground motion. I mentioned the issue became important after NGA-West1 when our friends in building code community, they recommended using rotated, maximum rotated ground motion. And for decades, we have been saying that fault normal is very important and fault parallel and so on. So a group of researchers headed by Professor Jack Baker at Stanford dig into the database, and the very interesting, well-focused report is out. One key conclusion is this, that if you are within 5 kilometers from the fault, within 5 kilometers, very close to the fault, and you are interested in 0.5 seconds and longer, then fault normal really is the direction of maximum component. If you go to beyond 5 kilometers, 10 kilometers, 20 kilometers, the maximum rotated motion, really the angle is random. That is really important. So your structure, you look at it 20 kilometers from the fault, not necessarily fault normal is your maximum direction. It's really random. And this is consistent with the other studies that they did it even pre-NGA, but that group nailed it down. The report is out, is a part of NGA-West2. Site response. This was a very important issue. The concept is this, especially for loss estimation community, that usually the loss estimation modelers, they take NGA-West1 or 2 or any NGA. They take the ground motion prediction equation for 760 meters per second for rock. So they exclude the site amplification terms that we have in GMPE. They get the results, and then they applied NEHRP site amplification factors that are in the building code for the last couple of decades to adjust it for different soil conditions. We know for a fact that the ground motion prediction equations, amplification terms, soil amplification terms, are not really 100% consistent with NEHRP factors in building code. So really it's like apple and orange. They take a part of GMPE, but the part that is site amplification, they don't use it, but they use NEHRP factors in building code. And since these are not consistent, it becomes a little bit issue. So a group of several geotechs headed by John Stewart at UCLA, they were digging into this issue in terms of data, in terms of various things. And eventually, they recommended a new set of NEHRP factors, site amplification factors. It went through a couple of layers of vote. Up to this point is promising. I think there are at least a couple of layers of votes will needed to become basically law of the land. It's not yet there, but it's important. If it goes through, really it means that we are recommending changing the building code eventually. One key feature is that always we talk about BC boundary, 760 meters per second is BC boundary. And I always, even when I started my practice many years ago, I said, if it's BC boundary, so how come B is 1? So it has to be B. Eventually, lots of internal debate, technical and non-technical debates internally and externally. The version that is so far is promising is that now B is not B, the site amplification for B is not 1, it's less than 1. The real site amplification for BC boundary, 760 meters per second, will become 1. That is consistent. If it goes through, it means the building code will be eventually, possibly changed. If that is true, really the NGA-West2 has 2 major influences in the entire building code community. Changing the NEHRP factors, as I mentioned, and obviously GMPEs that they go through the natural hazard maps, and Mark Peterson will mention. So really from 2 ways this project is influencing the entire earthquake engineering community. As I mentioned about NEHRP factors and BC boundary, and now class B factors are less than 1. There is a report that was final on that task. Ready, we submitted even to the sponsors. We didn't make it publicly available. The reason was we were waiting for the votes for the from building code community on those 2 tables. Now that we got positive votes, very soon we are going to publicize and publish publicly the report on site site amplification. Status of NGA-West2, I'm proud to say we are done. And I'm proud to say that we are done without even a single delay and 1 minute delay in the delivery. I remember in NGA-West2 early on, they grilled us, the sponsors, they grilled us that in NGA-West1 you guys were late and so on. So we really killed ourselves to make sure that we are not missing the deadline, and we didn't. So everything is available, really. The flat files are available. We published 13 peer reports so far, and there will be then the ground motion prediction equations. Obviously, as I mentioned, we are continuously in contact with the end users, including U.S. Geological Survey. Mark Peterson is going to talk about. They reviewed and they adopted 5 out of 5 GMPEs for the next revision of national hazard maps. We submitted many papers, publications for a special issue of earthquake spectra that will be published in August 2014. However, for various reasons, and earthquake spectra and EERI are pushing the things that if a paper, not only for our special issue, any paper that is reviewed, revised, accepted, they are not going to wait till 6 months to get the hard copy. Immediately they are going to post. We are really pushing to have most or possibly all the papers to be posted, hopefully by end of 2013. Many of the papers went through the second and third iterations, have been submitted, and they incorporated the review comments. So we are pushing in a month or so, we publish everything at the EERI website. The actual hard copy, you'll get it in August 2014. All the database issues, site response, directivity, directionality, and GMPEs will be published in that. There were many people involved in this project, exactly 32 people. Now you appreciate how much I suffered. I'm not going to read all the names, but I want to make sure that this is not really my project. This is not really a single project. It's a community project. Many people involved at various working groups, database, GMPE developers, vertical, horizontal directivity. It was, and many meetings, technical meetings, challenging meetings, and so on. It was really like solving a large pieces for a large puzzle through really coordination and technical and teamwork. Thank you very much for your attention.
Thank you, Yousef.